All right, so let's get started. I have the midterms graded, so I'll hand those back. Should have calculated an average, but I mean, I don't know what to say. I can tell who studied and who didn't study, I guess, is kind of the results of it. Some people did well, some people didn't. I'm probably not going to do test corrections just because I think things will shake out with the normalization. And again, just turn in all assignments. And then you will have, your take-home final. So I'm hoping since that's take-home, that'll help kind of buffer things out. And then we can always go over stuff on the midterm. Probably just wait for people to ask questions. 5 was really hard, the balancing one. People a lot of people didn't get that right, but. And then 6 was supposed to be easy, the like acid-base one, and there are a few tricks there, but like I said, I'll probably just hand them back, and then if I notice any trends of questions that come up a lot, maybe we'll go over some on Thursday. And then this week we have our radioactivity lab, so that should be fun. And so then that goes with our kind of hodgepodge chapter. So it was a little slow, but I did open up the notes this morning, and there should also be the interchapters posted online. And you should also be able to find the interchapters for free online, but if people need a link, I might have to post that. And then don't forget about the reading quizzes. So there are a lot of reading quizzes this week for all the inner chapters. So that's a little bit of work. So probably want to get started on that so you can read that and do the quizzes. All right, so then, like I said, kind of hodgepodge with these inner chapters. And so we're going to just touch back on radioactivity. I think we talked about it briefly when we discussed rate law, but we're just going to kind of remind everybody and recap. And so radioactivity, if we remember, is just the release of high energy particles and or high energy electromagnetic radiation from the nucleus of an atom. And then, of course, right, we can either discuss the different uses for radioactivity, obviously bombs, but now there's a lot of interest in doing nuclear power plants with radioactivity and thorium developments. And so atoms that eject particles or energy are referred to as being radioactive. And obviously, these radioactive nuclei spontaneously decompose over time in a process called radioactive decay, and these nuclei are unstable. And then just some definitions. So the parent is the one that's undergoing the decay, and then the daughter is always referred to as a new nucleus. And then if you remember, nucleides with 84 or more protons tend to be radioactive. So we could look at our P table. And then we also used to have a chart of the nucleides in lab, but it was kind of hard to see anyways. So now it lives in the stock room. But if you ever wanted to look at it, you could check it out. And so this is, so right, 84, so after polonium, they're radioactive. And you may remember that just historically. Something else you can look at, like I said, if you get really bored, if you look at a chart of the nucleides, then this just tells you all the different atoms. So this is essentially an interactive version of that poster. And so they have the atoms on the side. It's a little hard to see, admittedly, from this view. But for example, so here's cesium, and then it tells you what kind of decay mode for all the different isotopes. And so you can kind of scroll over. So cesium 116, 117. So you could really knock yourself out there. So that's kind of fun just to look at what goes to what. And so if we remember, at least I think we discussed it, there are kind of 3-ish main types of decay. We'll kind of clarify this beta particle. But essentially we have alpha particles, And so those are ejecting a helium nucleus, and we can write the symbol like so. And 4, of course, symbolizing the mass of it. And then obviously if it's helium, it has an atomic number of 2. And so we'll see that these can be easily shielded. And so if we remember, right, we have our, again, helium nucleus. And we'll see this in lab today. So it's the most ionizing but least penetrating. And so we'll see how we can stop the alpha radiation today. So we'll look at that. And so we'll go back to the equation in a second. And then if you remember, we had these beta particle decays. And so this is essentially electron-like. And so usually when we refer to beta decay, we're talking about negative beta decay. And so that's why it has a -1 charge, negligible mass, so just like an electron. There is positive beta decay, which again we'll clarify, but it's essentially a positron then, or anti-electron, so still massless, but then a charge of +1. And symbolized still with a beta. But again, I think I mentioned this back when we first talked about it, but I'll mention it again. So just be careful of whatever reference you're looking at. Again, they may or may not make a distinction, or they'll just call it beta positive, beta negative. So there could be different names for this. And then we'll look at gamma. So again, this is now just energy. So not a particle emitted, and we'll kind of see the symbol that goes along with the gamma. And so right, this one, it makes a caveat as sometimes it emits positrons. So again, sometimes they refer to it as positron radiation. I'm just going to remind us, okay, yeah, that was beta positive if we're calling it that. And again, right, positively charged electron-like particle. And then we could also have the case of electron capture. And so that's when an electron is pulled into the nucleus. And so we'll look at those nuclear equations. And then so now we can focus on the balancing and kind of remember how to balance these. And so if you remember, we make sure that all the top numbers add up to each other on both sides. So if we're beginning with 238, then our daughter and whatever we lost have to equal up to that mass. And so this is how you can figure out what the daughter is as well. So we could say on an exam, uranium-238 underwent alpha radiation or alpha decay. What is the daughter? And so then write 238 minus 4. So that gives us 234. And then 92 minus 2 gives us 90. And then, of course, we can just go to our periodic table and then look at element 90. Okay, that's thorium. So that's how we know thorium was our daughter. All right, so like we mentioned, most ionizing, but can be easily stopped by paper, clothing, and of course, again, balancing our nuclear equation means that our atomic number decreases by 2 and the mass decreases by 4. And so looking at beta decay, so we can formally at least kind of appreciate what happens. So a neutron would split off to a beta particle or electron-like particle. So it gets emitted and then create a proton as well. So we can see, right, how they add together to give us back our neutron. So a negative and a positive particle, and then the proton holding the mass. And so again, we'll play with this in lab today. But again, So we have beta decay, 10 times more penetrating than alpha, but only half the ionizing ability. And so you can still block it with like heavier cloths, or again, we'll see what other materials work. And then again, we'll just balance out the reaction formally. And if we're just looking at a neutron in this case, then, right, balance it out. So again, one on top. Obviously, it's split into a proton and an electron. Let's look at another classic example. So carbon-14 undergoes this type of radiation. And so then we can figure out, again, the daughter and kind of look at this hint here. So of course, right, our atomic number will increase by 1, and that makes sense, right, since we're creating a proton here from this neutron splitting. So now we'll go to 7, and again, right, add up both sides. So we have 6 on our atomic number, -1 formally on our product side, so then 7 has to complete the algebra expression. And then, of course, figuring out the mass. So the mass, right, remains the same. And then we see that, again, just by balancing the nuclear equation. And then 7 corresponds to nitrogen. Questions about this one? And so, again, let's do another one. So if we have phosphorus 32, so it undergoes beta decay. All right, so take a second. So what would be the daughter? Yep, so sulfur, excellent. So that'd be 16. And then what's the mass of sulfur for this isotope?
32 or for the isotope?
Yeah, it'd be 32. Okay. So excellent. So right, again, just balancing. And again, we see how our atomic number increases from adding a proton there. All right, so not too bad. And so now, looking at gamma. So gamma is a little strange. And so sometimes gamma may be with like, alpha or beta emission. Because otherwise, if you have solely gamma emission, so there's no formal loss of particles, so that, right, there's no change in the identity. It just kind of goes from a high energy state to a lower energy state. And so usually there's like a weird M symbol to kind of symbolize that, yes, this is a metastable isotope and it will undergo gamma radiation. So it may look like this. Just trying to see if I don't have the exact isotope, but I remember it's a technetium. Where is that? No, I can't even find the compound. I'm looking for CM maybe. Okay. Oh, there, I lost it. So I think it's curium that I've seen that's like that. where it's like this weird curium M. Oops. And then it would no longer have that. Oh, sorry, that was for the curium. So that would be some example, but again, it's not changing identity. And so least ionizing, but most penetrating. And so these are stopped by the lead plates or thick cement walls. And again, we'll play with that in lab. And so this one has positron, like I said, kind of segregated separately. So like I said, they refer to it as positron emission, but I'll just put beta positive again, since again, other texts may refer to it as that. And so it's essentially an anti-electron, so massless and opposite charge. And a positron is formed when a proton transmutes to a neutron. So this is kind of the classic positron reaction. And so we see, right, again, we emit our little positron then. And so now we lose an atomic mass, and then our mass, or excuse me, lose our atomic number, and then atomic mass is unchanged there. So phosphorus 30 goes to silicon 30 there. And then we don't often see electron capture, but you know, we should at least be aware of it. Sometimes it's used to initiate reactions too. So maybe start off with electron capture, make something unstable, and then continue. And so this occurs when an electron is pulled in to the nucleus. And so there's no particle emission, but we can see how kind of mathematically a proton and an electron will come together to make our neutral neutron particle. And so again, mass is going to remain the same, but now our atomic number will formally decrease by 1 as, again, right, that proton becomes a neutron. And then I think we've seen this summary table before, like I said in the past with other notes, but if people want this printed again, I can certainly do that if we need a fresh cheat sheet. So I see a lot of nods, so I'll get that going. This is what I was referring to, this element. I don't know why I couldn't find it. But again, right, so you just see the M here. So again, the M just telling you it's some sort of weird metastable isotope and transforms. Again, right, not changing the identity, so still technetium there. And so we kind of went over this already. So like we saw, these nuclear equations are super useful in describing everything. I think we saw that, how our atomic numbers and mass numbers are conserved. And again, the sum has to be equal, so that is useful. So we can do, let's do another practice. And so we'll just say, I believe this is radon or radium. Tell I'm not a nuclear chemist. This has to be radon. Yeah, so thanks. So 222 radon undergoes alpha decay. So see if you can write out what's the reaction of that. So what would be the daughter? And so what's the symbol for alpha again? Just remind me. Or, yeah, I mean, not that though, but like what does alpha decay mean again? Like the, this symbol. Because alpha decay is equal to, so what's its like mass, what's its number? Scroll back up if we forgot. Yep, there it is too. So right, what's an alpha decay mean? What are we losing? So 2 protons, 2 neutrons, so that would be a helium atom, right? So 4, 2. So we wanted to write our helium symbol. And so then we can figure out the daughter. So what would be the atomic number of the daughter? So that would be the mass, right? So 218 is our mass, and then what's the number? The atomic number, the 84. And then what does that correspond to? So now we need to look it up. Polonium. Oh. Excellent. Oh. So let's do another one. This one's kind of also simple. Should have picked harder examples. So now let's look at 172 AU undergoes alpha decay again. So what do we get for our products? I'll write at least what we started with. So we had to look up gold's atomic number and then alpha decay again. So then what's the daughter? Iridium. And so what's the atomic number of iridium? 77. And then what's the mass of this isotope? 168. Excellent. And so I couldn't find a good example offhand that was real, but we could also have on the exam, like it could make 3 equivalents of alpha decay, so then you'd have to take into account like 3 times 4 minus the mass. So just make sure that you balance it with the correct equivalents. But I'll try to find some examples. And so then we covered some rate law stuff, or at least that's when we went over it. So if we remember some rate law. What else was I looking for? So other things that we want to discuss are, so we can look at what's called our mass defect. And so the mass defect is just defined as the difference in mass between the nucleus of an atom and the sum of our separated nucleons. All right, so let's think about what this is saying. And so, right, this is essentially showing us where our energy comes from in these nuclear reactions. And so we could write out this equation, E equals mc squared, right? Everyone's pretty familiar with that one. And so we find that we can use our mass defect, so figure out, right, our missing mass, plug it into this energy formula, and so that will give us our energy. And so how this works, so of course, let me give us some numbers to work with. And so let's just take, for example, so if we want to look at bismuth 209, and so officially this isotope, so again, right, we have to look at the mass of just one isotope. So this isotopic mass is 208.9804 AMU. And then we go about analyzing it. So of course, now let's look at its components. So 83 protons, 126 neutrons. And then again, right, we'd have to look at some of our fundamental values. I just have it in my notes. So we have a mass of a proton is 1.007825 AMU. Mass of a neutron is 1.008665 AMU. So again, these are just looking up those fundamental values. And so now we can add this up and compare. So what it should be, right? So this is kind of showing us our nuclear binding energy. All right, so we get something higher, which is what we expect, right, from what this is saying. And so we get, so 210.74, I'm trying to keep as many digits, 741265 AMU. So, okay, right, we can already tell, obviously there's a discrepancy. But then we can find this mass difference. And again, this gives us, right, our nuclear binding energy then of what's being used, right, to hold that atom together. So now let's calculate our change in mass or mass difference, mass defect, right? How much is missing and where did it go? Well, it went into the energy, our binding energy. So mass defect of 1.7087 or so, or we can keep all the digits for now, AMU. And so now we have our atomic mass unit. And so I was just trying to check what units we are in. So let's look at, probably want to check our C squared constant. So right now we're in AMU. I was trying to find other units for us. Blah, blah, blah. There we go. Electron volts. Come on. You're not going to give us. I'll have to find where it comes from. That's annoying. All right. Essentially, because again, I have it in my notes here, but I wanted to show you where it came from. So C squared is 931.5, and that's going to be mega electron volts. But again, right, we have to figure out where that came from. So obviously, right, the speed of light is usually given in meters per second, and then that'll be meters per second squared. But then this is related to joules, right? So joules, if we recall, is kilograms meters squared over seconds squared. So I was trying to figure out how we get it into our electron volts to move with our AMU, but I didn't have the answer offhand. So like I said, we can use this though for now. So C squared is equal to this constant factor, again in mega electron volts, to be in the appropriate units. And so now to be in these units, we can continue with E equals C squared. And so now we can plug in the AMU mass, which again is the trouble with why I didn't pick, right, our normal speed of light. So I guess we could have converted it to kilograms, and then that would give us in joules. But so then just plugging it in for these mega electron volts for now. So 1.760865, again, atomic mass units. And so now we have our total energy is 1640 mega electron volts. And so you could also, it may ask you to say, like, what's the average energy per nucleon. And so all that means is, okay, right, going back to what isotope number it was, so bismuth 209. So again, right, that's just our total number of protons plus neutrons, so total nucleons. And so then we can divide it by 209. And so say it's about 7.84 mega electron volts per nucleon. So that gives us a rough idea, right, of, again, our binding energy per nucleon. Questions about that? All right, so now we're gonna switch. Well, actually, sorry. Let's see if we have some. We'll save our nuclear equations. All right, so let's kind of shift gears, although it might be a good time for a break. So I know it's a little early, but let's go ahead and take our break because we're about to shift to OChem. So we'll just take a 10-minute break. I'll hand out the exams, and then we'll continue with the rest of our inner chapters there. They're not curved yet, so I don't curve anything to the end. And then everything's normalized. All right, I think we've made it back from break. And so like I said, we're going to shift gears pretty much and cover now OChem, or at least a brief kind of introduction to OChem. So if you're going on right to OChem next year, this is a good kind of introduction at least. Otherwise, it's a good general overview since, you know, organic molecules make up a large portion of chemistry. And so alkanes, and notice, right, we have the ANES. So alkanes refer to any chain of, and they're going to be carbon and hydrogen molecules. And again, this anes here is telling us that we have no double or triple bonds. So just the simplest kind of straight chain. Sometimes this is referred to as being fully saturated. And all that means is that it has all hydrogens on the carbon. So again, right, no double, triple bonds. So there's going to be hydrogens everywhere. So that refers to saturation, which does go to saturated fats, which we could talk about as well. And we'll further clarify this. So now we're just going to look at acyclic alkanes and kind of the formula. And so a cyclic alkane would be obviously a circle. So something that looked like so. So that would be a cyclic alkane. But then it would have a slightly different formula. So acyclic would then just refer to any sort of straight chain or branched. And so any alkane has this general formula. So CN H2N plus 2. So you always have 2N plus 2 more hydrogens. So for example, if we want to look at hexane, and well, now I'll reveal. So we have these prefixes here, and of course it can go on and on and on. I just showed the most common ones. So we have meth for 1, eth for 2, prop for 3, but for 4, pent for 5. Hex then is 6, so that's hexane, meaning a 6-carbon chain. And then we have heptane, octane, nonane, decane, undecane, and dodecane. And it, again, obviously continues. So hexane is C6, and then we can follow this formula. So then H14 would be our expected formula. We can draw it out. And so again, now we can remember how to draw things out. So O chemists often use the shorthand with the lines. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so my biggest advice for OChem is count and then count again, since always messing up a carbon can change your whole answer, obviously. So OChem professors are pretty strict on your carbons and carbon counting. And then we can translate this. So I'll just kind of rewrite it again. 1, 2, 3, 4, 5, 6. Oh, that was kind of terrible. And again, in your mind, you're filling in every carbon such that it has 4 bonds. So these N ones have 3 hydrogens. Any middle are paired to 2. And we could count them up, verify our formula. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And of course, you may also see it written out in this form. So 1, 2, 3, 4, 5, 6. And so, you know, obviously this is kind of clearer in some ways, just to see what's going on. What I want you guys to keep in mind, though, is I really want you to be thinking about the 3D structure of these at all moments. And if you really come in with that sort of mind frame to OChem, that will really help you, since understanding the 3D spatial relationship is kind of the hardest thing in OChem, but it's really important. And so again, just kind of staring at this hexane, so appreciating all the different representations. Again, obviously our lines. But then what's kind of nice about either one of these models, either the space filling or our more ball and stick one here, is again, we're appreciating that every carbon in this case is tetrahedral. So again, just think about its 3D geometry. So that's kind of why you draw it zigzag too, right, to kind of show its true space relationship. It's always good to keep in mind. Oh, that being said, I should have pulled up, this is something else that I should post. So there's all sorts of different molecule kits. I'm trying to find what I call the baby one. Yes, I found it. So I'm not a biggest fan of like the ones we have in class, actually. Like they're okay for Gen Chem, but I don't really find them that helpful for OChem, or rather they get kind of bulky. And so this is my absolute favorite molecule kit. I need to bring it in on Thursday. And so it's this little Maruzen kit, and what's kind of nice about it is all these, the carbons already assembled, like their stereochemistry. And so you just pick kind of sp3, obviously down there, or these are sp2 carbons. And then it just helps you build your organic structure a lot faster. And so, again, you know, you probably don't need it in this class, but if you're thinking about going to OChem later, you might want kind of a nice kit there. I'm just gonna, because there are other forms too, but I don't like. Let's see if I can pull up the other style that's pretty popular, but surprised I'm not seeing this other one. Okay, I'll look for it and then I'll show you kind of what the issue is. And so again, kind of going back to the saturated hydrocarbon deal. So again, kind of thinking of like dissolves like. Obviously, these are going to be pretty nonpolar, but then we can see, let's just pull up a saturated fat. That'll kind of help. And so if we just kind of look up what a saturated fat definition is, it is literally that, right, where it has all single bonds. So again, that's what it's referring to. And so again, what kind of makes saturated fat, or gives it some of its properties, right? So if you think about saturated fat, sometimes they tend to be more of a solid at room temperature, and that's because of this nice stacking feature, right? So then it can kind of really stack, and there's no kinks in the chain, as with, right, an unsaturated hydrocarbon. And so because it can kind of stack like that, and that makes them solid at room temperature. And so undecane, we could just practice drawing it. So again, whatever style, I prefer doing this little stick method if we're going to draw undecane. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then again, just always kind of recount in your head. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Really cannot count too many times. And then I'm just drawing the straight chain. So really you could have other isomers, which we'll discuss. And so now we just want to make sure we can kind of draw our simple molecules. I think everybody hopefully knows methane by now in here. And again, appreciating that our carbon is sp3 hybridized. Again, every carbon has a tetrahedral center. We want to be thinking of our geometry. And then ethane. So of course we could just draw it like a line or draw out kind of its structure here. Not the best structure. And so other things to kind of think about, but we don't need to get too deep into this class, but you will in OChem. So with these single bonds, you have a rotation. So right, you can rotate around the center. And so this also leads to different conformers. So right now I drew it kind of in the most stable. And so that just means that, right, we have one on top. On this side, two on top, so it's kind of gives it more space. Pull up a better picture of what I'm referring to. So this is basically what you'll see in OChem, this graph here. And all we're saying, and all I want y'all to appreciate is, again, rotational freedom. And this is looking at more specifically butane, which has other considerations, right, since one of them is a methyl group. But again, we're just saying it can rotate around. This causes different energy strain. And so the most favorable is kind of how I drew it, where again, they're all kind of spaced out here. So that's what's going on here with the ethane. So 2, 1, 1, 2, to kind of make sure they're all spaced out. So again, this would be called the eclipsed conformation that I drew, but kind of, we'll say that for OChem. And then propane. So propane is 3. So again, we could draw it 1, 2, 3, just this little stick. You can draw it in a line, just as long as we can understand all different forms of it. So there's our propane. Again, right, formula follows C3H8. So following the 2N plus 2 rule we saw. And so butane, so now we'll draw out, we'll start to get into some isomers. So butane, so first I'll draw out N-butane. So that just refers to a straight chain. So 1, 2, 3, 4, so butane being 4. So C4H10 then. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so that makes sense. And so now we can look at other, what are called isomers. So we'll define it in a second. And so some of them have names. So in this case, we have isobutane. And so iso refers to this kind of 3 group here. And so then this is 1, 2, 3, 4. So this is isobutane here. And so it still has the same formula, right? C4H10. And so we can add our hydrogens to make it explicit. So of course this one needs 1 hydrogen, and then all these other methyls have 3 hydrogens. So still C4H10. And so then we can just define our structural isomers. So we'll come back to isomers. We'll look at different forms. But they're just defined as isomers, so basically compounds that have the same chemical formula but different connectivity. And so we can see this in a bunch of different groups. So we could have, right, ethers versus alcohols or something, or obviously in this case, right, straight chain versus branched. But again, you can get all sorts of permutations once you get into oxygens and other variables. And then kind of starting to look at a few reaction types, at least slowly. So of course we know that organics undergo combustion reactions. And so again, just kind of the general formula. We have some carbon, some hydrogen, some oxygen, and then react with oxygen to always give us CO2 and water. And then we can just draw a more specific example. So then one example is just our combustion of propane then. So plus 5 oxygens to give us 3 CO2 and 4 water. And so again, right, we've seen that. Obviously, these are fun to balance. So other reactions that can happen with these hydrocarbons are called, so this is called a substitution reaction. And so we can tell that it needs some energy to drive it. So actually this is a radical mechanism, which might be too much information. But these are pretty cool. So we have methane, and then of course plus chlorine. And so since we have, again, this radical initiated reaction, so what this UV light does is it helps to split this bond, and it splits it in half, creating a chlorine radical that can then go on and react and obviously break this bond and make our chloroform product there. And so we'll look at a few other reactions. And then again, we'll just make a note, right? Don't forget about hybridization. And so we just want to at least appreciate some classic OChem examples that we'll see. And so SP, one of our classic examples is CO2. Of course, right, just remember the structure, it's linear. We can think about the orbitals that go into it, right? 1s plus a p. So SP, so again, right, they're both in line there, so kind of clearing the cobwebs. Usually we call this PZ, right, for our principal rotation axis. And then SP2 hybridized molecules, so remember we had like those ketones typically tended to be sp2, so again, planar, or trigonal planar, we should say. So again, just thinking about the geometry, thinking about how it can be attacked to from either side since it's planar. I'll also put in here, right, some of these double bonds. We'll get to it. But so benzene is special. So we could look at benzene. We could also think about, I should have drawn like graphene out. That also is an sp2 hybridized. So this is benzene. Again, sp2 carbon. Graphene is a good example of sp2 carbon. And let's actually look at a picture of graphene. So not crazy about their picture, just because it doesn't show good bonding, but again, graphene is just kind of 2D, so that means that again, right, sp2 hybridized for all these, so just thinking about the properties of graphene. Again, we've kind of mentioned it, right, that it shears off in layers, but again, we just want to think about how that relates back to that sp2 hybridization there and how it's planar. And so, again, benzene, I just like looking up the pictures so we can, again, appreciate the true 3D nature. So again, benzene, nice sp2, so planar, so we can tell, right, it's planar there. And of course, sp3 is our usual carbon center. I'll just draw methane, but of course, it could be bonded to all carbons, could be diamond as well. So remember, diamond is tetrahedral. So tetrahedral geometry. Again, we're not trying to so much get into it in this class, but I at least want to prepare you, right? So again, you're kind of thinking tetrahedral, how can it react versus these kind of planar complexes, so that leaves these planar ones kind of more exposed in some ways. Questions so far? All right, so we'll keep looking at some OChem business. And so now we have what are called these functional groups. And so again, these just kind of help us name our organic compounds, or if we were talking about drug design, we might refer to different functional groups. And so of course, we'll start with meth or methyl, right? So our methyl group is just a little CH3. And again, I like to remind everybody about amphetamine versus methamphetamine. And they are literally just different by a little methyl group. And so let's look up, right, our organic structure. So there's amphetamine. And then again, all we have to do to make meth is then you methylate this little amine here. And so now let's go to methamphetamine. And again, appreciate the structure and the difference and the relevance in drug design. And so again, right now it just has the little methyl group there attached to the nitrogen. So So that's the only difference, but again, that's what allows it to cross the blood-brain barrier more easily, and so lower dosage. And then again, ethyl group. So typically you don't, I mean, I'm not the biggest drug design chemist, but typically you don't really see like ethyl groups put on there like methyl groups. They don't have quite the same effect since methyl is a little smaller. And then propyl, obviously a 3-chain. Isopropyl refers to, again, this sort of 2-prong with the 3 there. So right, 1, 2, 3 carbons is our isopropyl group. Fluoro. So again, fluoro is good for medicinal chemistry. So it's similar to a methyl group. And so that's why, you see a lot of fluorine compounds in drug design. And so we can have fluoro, chloro, bromo, and iodo groups. So all of them have their place in synthesis. So if you kind of remember right from the activity series, so obviously higher halogens can kick out lower ones. So iodine is useful, especially for like beginning parts of the synthesis. So that goes back to why iodine is a regulated substance, because it could be a precursor to meth to help you substitute a methyl group. And then, like I mentioned, right, fluorines kind of show up in the final product. And then obviously amines are pretty important in chemistry, and obviously they have biological relevance. So if you notice, there's a lot of drugs that are kind of similar to tryptophan. So of course tryptophan is one of your amino acids. So let's pull up tryptophan. So tryptophan, it has both an amine and then a nitrogen in its framework as well. Again, many drugs are derived from tryptophan. So I was trying to pull up. So for example, to get into drug chemistry, but DMT is one of the drugs that would be derived from tryptophan. So you can kind of see they're pretty similar in structure. So they just replace the carboxylic acid at the end with an amine there. So just kind of interesting to note. And then nitro groups. So we see a lot of nitro groups, again, in like synthesis, but nitro compounds tend to be toxic. So let's pull up if I can. I'm trying to find, I think it's nitroazobenzene. It's some horrible colored compound. Trying to find a nice picture of it, because a lot of these nitro compounds are colored and very bright. I'll try to find some later. The internet's failing me. And then our other kind of common group is a phenyl ring, which is a basis of our benzene ring. So this, again, back to the sp2. And it can be substituted right with alcohols or nitros, if I could ever find any good example or pictures online. All right, so then we'll try to work on some naming in this class. And so this is, again, kind of more for simple organic molecules. So obviously right? If you go on and make your own molecule, you can call it whatever you want and come up with little acronyms for it, which usually is what happens. And then obviously somebody gets to name the designer drug. And so let's look at these rules, and then we'll play around with these chains. And so for our rules to name them, we have to identify our longest chain. And so this is kind of weird, because when we say this, we're going to have to like step back and analyze a whole molecule, and your longest chain could curve. So you want to see continuous chain, and again, we'll practice that. And then we'll identify and name any groups. So again, we'll kind of practice that. And then we'll number the chain, so starting at our nearest substituent group. So again, we'll have to go through some of what that means in our examples. And then we'll see what we mean by designated. So after we number it, we'll use our numbers to show where our groups are, and then we'll assemble the name, listing our groups in alphabetical order, and of course using our prefixes. All right, so that kind of sounds pretty confusing. But what we want to do is we want to at least just draw our structures for all the possible isomers of heptane. And so of course let's name the easy one, so it's drawn here. And obviously straight chain, so 1, 2, 3, 4, 5, 6, 7, right? There's no weird branching. So 7 is our longest chain, and then obviously no groups on it, so heptane. So maybe don't get bogged down so much in like trying to name it, but first just try to sketch out all the different types of structures, right? How can you draw out C7H16? And remember, keep it linear, right? So it can be branched, but what I'm saying is don't make any circles or stuff. And then obviously keep the single bonds, but just see if you can sketch out our isomers. And then we'll probably put them on the board and play with them. We'll look at the naming. So does someone want to draw just a structure on the board? Of course, if you go first, you get to pick the easy combinations. Yeah, go for it. So yeah, just draw it and then we'll work through the naming of it together with the rules. That one's good. So 1, 2, 3, 4, 5, 6, 7. All right, so I think that works. So I'll draw it out. So just kind of modifying our heptane. So 1, 2, 3, 4, 5, 5. Oops. So I think this looks like what you drew, right? 1, 2, 3, 4, 5, 6, 7. All right, excellent. So this looks good. And so now let's go through how to name it. And so going back to these rules here, so it says, okay, find the longest continuous chain. And so in this case, it doesn't matter, right? We could go 1, 2, 3, 4, 5, 6, or starting here, 1, 2, 3, 4, 5, 6. And I'm just going to fix this bond because it looks, oh, that didn't make it better. 1, 2, 3. All right, so it looks like we have hexane then, right? So that's kind of our first step, is identify our longest chain. So either way, it was 6. And okay, so then it tells us to identify and name groups attached to this chain. And so of course we're just playing around with our hydrocarbons. And so this is our methyl group, right? Okay, so now we have a methyl. And so now it asks us to number the chain. And so what this means is we want to assign what's called the highest priority to our substituent. And whichever substituent has like the higher priority, which we'll get into, so like mass would dictate. And so in this case, we don't have any other competing groups, so we just have the methyl group. So we want to assign it the highest priority, which means we want to assign it a 2. So I'm going to label this 1, 2, 3, 4, 5, 6. So again, it should be 6, matching our longest chain. So then this tells us the position of the methyl. So right, this is 2-methyl then, since our methyl is hanging off of the 2 position. And so again, that's what it means now to designate the location. And so now we can finish naming it. So putting it all together with our groups. So again, we only have one group. So 2-methyl hexane is the appropriate name. And then just watch that you don't draw the same thing, which happens a lot in OChem, right? So we can't move this methyl group over here and say we have 5-methylhexane, because it's the same thing by rotation, right? And we wouldn't want to give that methyl group such a low priority anyways. All right, does someone want to draw another isomer? Again, go early so you can take the easy options. Just have to draw it. What else could we do? You could also describe to me any shape if you don't feel like coming up. What else could we do to it? Maybe even looking at this hexane, because could we do anything else? Could we make any other isomer hexanes? So we said we couldn't move it to the 5, but could we do something else? So 3, the problem with the 4s and the 4 is the same as 3, right? So 1, 2, 3. But we can do 3 methylhexane. So let's draw that one out at least. So 1, 2, 3, 4, 5, 6. And then 1, 2, 3. So I'll stick my methyl group there. And then let me just double count. So 1, 2, 3, 4, 5, 6, 7. So just making sure I didn't mess up there. And so now I'll just number it again, assigning our priorities. And so again, right, the 4 is the same as 3, so it has to be 3-methyl hexane there. Right, other permutations, you can draw it on the board. So we still have, I think we have 6 more to go because there are 9 of them, and we have 1, 2, 3. So you want to do, so let's do 5, so 1, 2, 3, 4, 5, and then you want to put, did you say like an ethyl on there instead? Yeah, well, let's try it. So we could do, let's see, we could do 1, 2, and I think that would work. So 1, 2, 3, 4, 5. So that's still our longest chain, right? 1, 2, 3, 4, 5. We could go this way for the longest chain, right? So just kind of notice that it doesn't matter which way we go. They're both 5-membered chains. It's kind of confusing. And so now let's label it so it doesn't matter in this case, right, whether I went 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5, it's still 3. And then now we have 1, 2 for our ethyl group. And so now this would be 3-ethyl pentane. Okay, good. What other variations do we have? So kind of think about how else we can manipulate it, right? We're probably done with the hexane structures. So what else could we do to pentane? Ethan, do you have any thoughts?
With the methyl hexanes, it's not possible to do a 4-methyl group?
No, because that would be the same, right? Because then you'd want to assign highest priority. So yeah, 1, 2, 3. Well, what else could we do? So I think if we put the ethyl back on 2, it makes us a 6-member chain. So let's kind of, we can play with that though. Oh, that was weird. Thank you, technology. Yeah, I got so upset for some reason. So let's, again, try to sketch out. So 1, 2, 3, 4, 5, 1, 2. But then if we look at our longest chain, it ends up being 1, 2, 3, 4, 5, 6 again. So then it's 1, 2, 3, 3-methyl hexane again. That doesn't work. But yeah, that's why this is tricky, but it's good. It's good to sketch it out, right? So you can just write it out. Oh, okay, well that was 3-methyl hexane. Same thing. So keep testing them. Bonnie, do we have any ideas? We could still play a lot with the pentane. So we have our like pentane framework. We stuck an ethyl on there, but then what else could we do instead of combining them into an ethyl? Yeah, so put 2 methyl groups on there. So where do you want to stick them? And there might be a few permutations. So you want to do 2 and 4 first? Yeah, so let's do that, right? So we can probably do 2 and 4. So that looks good. Again, just double check that that's still our longest chain, the pentane. And it appears to be so, right? 1, 2, 3, 4, 5. So even if we go that way, it's still pentane. And then again, assigning priorities, it doesn't matter if we start 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5, right? Each way our methyl groups get the 2 and 4 priority. And so again, we have 2 methyl groups there. And so now we can say we have 2, 4, and then this is where the dye can come into play since we want to indicate we have 2 methyl groups, and then the 2 and 4 tell us which location. So 2,4 dimethyl pentane. So that's one permutation. What else can we do with this pentane?
It's possible to do it on 3 and 5.
So let's see. So I don't know that 3, 5 would work. So let's kind of, because if we did 3, 5, that would make our longest chain. So that's back to 3 methyl hexane. But what can we do instead of 3 and 5? What other 2 numbers? So yeah, so if we do 3 and 4, that'd be 2 and 3, which I think that would work. So let's do 2 and 3 to give us highest priority. And again, double check our chain. So it's still pentane, right? I can't make a longer chain. So that's good. And so again, assigning priority so the methyls get the highest number, 1, 2, 3, 4, 5. So yes, that's 2, 3 dimethyl pentane. What else can we do with it? There's actually 2 more permutations with this pentane. We've stuck them on different carbons, but what else could we do? Link, do we have any ideas of what else we could do? What if we stuck them on the same carbon? Can y'all see some possibilities for that? So what are, we kind of have two options, I would say, to give us our last two pentane permutations. So where could we stick our methyl groups?
On the 2 and on the 3.
Yeah, so let's try that. So we could do 2, 2. And again, let's just make sure that we still have a 5-carbon chain, right? 1, 2, 3, 4, 5. So even if we go up, okay, it's still pentane, so that's good. So either way, and again, highest priority. So now we have 2, 2 dimethyl pentane. And then we could do it to the 3 position as well. And then again, right, the 4 is the same as 2, so just keep that in mind for symmetry. And again, double check that you can't make any longer chain. 1, 2, 3, 4. Okay, that didn't work out. And so then that's 3, 3 dimethyl pentane. All right, that looks good. So I think we're done with the pentanes. And then we're just missing, I'll give you a hint, the butane isomer. You might have to figure out how to shove all those methyl groups on there. So see if you can come up with a butane one and maybe the name. So you said 2, how many on 2? Yeah, so you could do 2 on 2 and 1 on 3. That's, I think, the last one. And so, right, you really can't play with it in any other way. So, of course, assigning priority 1, 2, 3, 4. And so you want to assign the one that has the 2 groups to the 2. So even if you had tried to draw it the other way, where you put them over here, right, 2, and then 1 there, so then you still would label it 1, 2, 3, 4. So either way, we should get 2, 2, 3, trimethyl butane. And then we really can't do anything else. We could try to, play with it. All right, what happens if we stick, an ethyl group there, but then look at what it does to our chain. So 1, 2, 3, 4, 5. So right now we're back at a pentane. So it looks like 3-methylpentane. Right, 1, 2, 3. So that didn't work. So yeah, I'm not seeing any other permutations that we could do with it. And I believe that was all our isomers. Did we get them? Yeah, so we got all 9 of them there. So that was good. So that's a good kind of exercise. And again, right, the point is kind of guess and check and draw. And then check your chain again. So that's always good to do in OChem. And then we're basically out of time, but I just wanted to show, again, some of those compounds, the nitro compounds, and what they do with the dyes. So this is methyl red, which is actually an indicator that y'all use. But what's kind of interesting is, again, it has this like azide bond here, so this nitrogen-nitrogen double bond, so that's kind of what leads to these highly colored compounds. And so this is what it looks like. Let's see, I also wanted to show, so I was mentioning that these nitro compounds tend to be colored. So the nitro ones, once you stick the nitro group, again, tends to make them kind of more colorful. And then obviously this one has an amine and a nitro. So these nitroanilines are used a lot in synthesis, but also a little toxic. And then amines technically should be colorless, but they're pretty sensitive. And so amines tend to degrade and make nasty brown, who knows what side compounds. And often you have to re-clean them or re-purify them before use. All right, so that's a good place to stop. So we'll continue on Thursday with alkenes, alkynes, so looking at more organic groups and just kind of working on our future knowledge bases. And then, of course, we'll have our quiz on Thursday like usual. And then otherwise, I will see y'all for lab. So I'll hang around in case there are any questions, but otherwise, see everyone at 1:30.
Can I give this to you?
Oh,
for all
yeah,
lives?
thank you. Your name's on there.
I think so.
Sweet.
Thank you.